Beginning of the 21st century, the Predator drone changed the nature of air warfare. Before, military air operations were very complex. Aircraft would have to go out, photograph and document an enemy target. They would bring that information back, had to be processed and interpreted. Missions had to be planned. Aircraft sent out on strikes. Other aircraft would go out and document whether those strikes had been a success. That process might take days or weeks. What the Predator does is it does that in real time, and it can do it with it being controlled from the other side of the planet. This has completely transformed both international relations and modern military operations. The key technology is the satellite data link. It is a low latency data link that operates through satellites. It allows full control of that aircraft to see what it sees. Weapons can be fired, all at nearly the speed of light from the far side of the planet. Just an amazing transformation in air warfare. Another key technology are the low aspect ratio wings that allow this aircraft to stay aloft for upwards of 40 hours at a time. It used to be in a military operation, you have a high-speed jet come over, and it might have a few seconds to kind of look at the scenario that's unfolding on the ground, decide what's happening, who to engage, and release the weapons. And of course, that led to a lot of mistakes and serious consequences. Operators now have the ability to loiter for a long time, be able to survey what's actually happening on the ground, and make much more sophisticated decisions about what to attack. The weapons employed are also very precise and have a limited potential for collateral damage, which has made these aircraft so critical to operations overseas, and it has transformed both international relations and modern warfare.
The automation capabilities of modern commercial aircraft are stunning. For example, once a commercial airliner has begun its takeoff roll, it's possible for the aircraft to complete the entire flight all the way through to landing without the pilot ever touching the controls. The onboard flight management system, along with an autopilot and an auto land system, is capable of guiding the aircraft through the national airspace based on the navigation aids, following the intended route programmed in by the pilots. In fact, when the outside visibility is extremely poor, this level of automation is required for continued flight operations, with help from the air transportation network that we described in the previous lecture. When the conditions are as low as 150 feet runway visual range, a suitably equipped aircraft can fly what is called a Cat 3B approach all the way to landing. Under these procedures, the aircraft lines up to land on the runway based on radio signals provided by the airport facility. The precision of the aircraft trajectory along these radio waves is within just a few feet of the desired glide path. And aircraft equipped to fly Cat 3B approaches have radio altimeters installed that very precisely sense the aircraft's height above the ground as it comes in on short final approach. These sensors tell the autopilot when to flare the aircraft for a smooth touchdown at the perfect spot on the runway. The aircraft is then slowed while the aircraft is on the runway centerline, and the pilots take over and taxi for the remainder of the distance to the gate. The level of reliability of this autonomy is so high that the pilots are generally required to keep their hands off the controls while flying a Cat 3B approach. Instead, they sit there and carefully monitor the progress of the aircraft to make sure that everything is proceeding according to plan. This so-called auto-land feature is so accurate that the system typically performs better than a pilot who's manually flying the aircraft. This allows the aircraft to safely land, even under conditions with absolutely no visibility. The biggest challenge, then, is actually being able to taxi from the runway to the gate under near-zero visibility conditions. So these automated systems clearly improve the safety and reliability of flight. An unfortunate side effect, though, is that these high levels of automation can lead to a deterioration of a pilot's stick and rudder skills, the ability to manually fly the aircraft. One example of this dilemma is the crash of Asiana Flight 214 at the San Francisco International Airport on July 6, 2013. The weather was just about perfect on that Saturday morning. Clear skies, fantastic visibility, and light winds. The kind of weather that most pilots dream of having. The only problem was that the vertical guidance for the instrument landing system was disabled for the runway. It was undergoing routine maintenance, so the pilots didn't have the precision navigation that they were normally accustomed to. But it shouldn't have mattered. Since it was such a beautiful day, they would have been able to line up with the runway from miles away. Also, the pilots didn't seem to fully understand all of the nuance of the complex auto throttles on their Boeing 777-200. They set up the aircraft for a manual approach, but with, so they thought, the auto throttles engaged and set to hold the correct airspeed. However, they ended up flying the approach with the engines set to idle due to some misunderstanding of the way the automation systems were set up. As they continued on the approach, the aircraft's speed began to decay due to the lack of thrust from the idling engines. Close in, the speed dropped more than 34 knots below the recommended approach speed of 137 knots. This led them to fall short of the end of the runway as they were just a few seconds from landing. By the time the crew recognized their low-energy approach attitude with low speed and low altitude, it was too late. They attempted to perform a go-around by throttling up the engines to maximum speed. However, aircraft engines can't spool up instantaneously, and the response was too late. The 777's landing gear slammed into the seawall at the end of the runway, causing the aircraft to careen out of control down the runway. So this incident reveals a number of challenging aspects of automation systems. On the one hand, autonomy enhances safety by allowing the pilots to land a complex aircraft in poor weather conditions. However, sustained reliance on automatic systems results in atrophied piloting skills. Furthermore, the functionality of these automated systems is becoming highly complex, such that even experienced human operators have difficulty knowing the complete behavior of the system in various states. The Asiana 214 crash might lead us to wonder, will increasing the level of autonomy actually help things? Could engineers design and implement some kind of self-aware system that would keep the pilots from making such grave mistakes? Or would it be better to remove the human from the loop entirely? This sounds like an attractive idea at first glance, but the difficulty of automation is that there will always be humans involved, and the interaction between humans and automation is a dynamic interface that is prone to failures. This aspect of human involvement is also the case for unmanned aircraft, or drones, such as the U.S. military's Predator and Global Hawk drones. While there is no pilot on board these aircraft, there is most certainly a pilot on the ground guiding the aircraft and making decisions. In fact, the drones that the military uses are more properly thought of as remotely piloted aircraft, since there continues to be a pilot involved. And these pilots are still very much a part of the action in armed conflict. The RPA operators, as they are called, describe the warfare that they engage in very intimate terms. Using the high-resolution cameras on board their aircraft, they spend hours upon hours surveilling and tracking their suspects, observing and getting familiar with the person's daily habits, friendships, and interactions. When the time comes for a military commander to make the critical decision to launch a strike, the RPA pilot is the one who actually pulls the trigger to launch a missile towards the person that they have been tracking for weeks on end. Then, after a full shift of surveillance and launching missiles, the RPA pilot, who is often based in the US, will go home to his or her family and participate in daily life, such as joining family for dinner or taking kids to soccer practice. This turns out to be a jarring shift in realities, where the pilot is engaged in armed combat one moment and then relaxing with family the next. This dynamic has been virtually unthinkable in the history of armed conflict, but is now a reality with these remotely controlled aircraft. And there is actually a huge crew involved in each RPA flight, even though no one is on board the aircraft. For example, the Reaper drone requires a ground crew of over 100 people to support the mission as pilots, sensor operators, launch and recovery personnel, mission control, and maintenance staff. There are many people involved, and this is why the military tends to avoid describing these aircraft as unmanned aircraft, unmanned aerial vehicle, or UAV, or an unmanned aircraft system, or UAS. Remotely piloted aircraft, or RPA, is somewhat more accurate, and then there's the simple moniker drone. While each one of these terms has various proponents with various good reasons, all of them essentially mean the same thing. For this lecture, I'll take a casual approach to the nomenclature using drone, most often due to its monosyllabic simplicity. The use of drones in military conflict is particularly attractive for obvious reasons. Clearly, the mission commanders can operate the drones much more aggressively in contested areas, since they only have to worry about the cost of the hardware, rather than the protection of a human life on board. And the performance limitations on military aircraft imposed by the human body, such as G-loading limits, are also removed. So any job that is dull, dirty, or dangerous is done very well by a drone. But there are also some less obvious reasons why drones have advantages over aircraft with a pilot on board. First, we've seen that vehicle weight drives many performance parameters, such as endurance, range, and so on. If we remove the requirement of a 200-pound pilot from a small-scale vehicle, that can represent a significant fraction of the overall vehicle weight, leaving more room for fuel or payload. So the payload and performance characteristics of drones will be much better than equivalent manned aircraft. Second, some aircraft designs are geometrically constrained by the need to carry a pilot on board. These constraints can include sufficient fuselage volume to carry the pilot, or a specific position of the pilot within the aircraft, which would be dictated by visibility requirements for the runway. Both of these pilot integration challenges often drive the cross-sectional area of the fuselage, which leads to higher drag. So removing the pilot from the aircraft design can substantially reduce parasitic drag, which has an impact on nearly every aspect of aircraft performance. Third, by moving the pilot from the aircraft to the ground, we can remove the physiological limitations encountered by all pilots. For example, when a pilot reaches a personal endurance limitation for fatigue or other physiological limits, it's a simple matter to hand off control to a new pilot and continue the mission uninterrupted. With drones, the range and endurance limits can be extended to match the amount of onboard fuel. And if a drone is capable of refueling in flight, then in principle it's possible to keep the drone aloft indefinitely, coming down only for maintenance. Fourth, cargo aircraft and military aircraft that no longer routinely carry passengers can be designed with lower margins of safety, since there is no human life on board that must be protected. This allows the designer to employ slightly riskier design choices on structural members, for example. So what are these dull, dirty, or dangerous jobs that drones can do? Drone applications can be placed into two categories. First, there are the applications where piloted aircraft have been doing the job, but safer, cheaper, or more reliable operations can be achieved. This includes surveillance, aerial photography, crop dusting, and certain kinds of infrastructure inspection. And we can envision unmanned aircraft flying transcontinental cargo flights, the kind of tedious flying that doesn't require a pilot's full attention for most of the flight. Second, are new applications that would not be possible without drones. Examples include small-scale local delivery, the idea of ordering a medication or a new cell phone or a latte and having it delivered immediately to wherever you are. Any method that makes it easier and faster to get something we need or just satisfy our consumeristic tendencies will be incredibly popular. Also, aerial imagery, such as real estate marketing videos, is being transformed by the unique vantage points that were never before possible until small-scale drones came along. And close-in inspection of critical infrastructure can now be done more safely and efficiently using drones instead of putting people in harm's way. For all of us, drones offer a unique vantage point that has never before been possible. Our sense of wonder, exploration, and adventure is kindled by the aerial panoramas that a drone can record. It's almost like being a Peter Pan, to experience travel vicariously through inaccessible places. Not even manned aircraft can provide the visceral experience of soaring under the canopy of trees, hovering above a fog bank in an urban landscape, or flying through sea spray along a rocky cliff. It's as if drones can unchain us from the bounds of Earth to see things in a way like we have never experienced before. And on top of all that, drones are equipped with feature recognition, allowing the drone to autonomously track its owner and record anything that someone does, from any number of unique angles. It's like the ultimate selfie camera. So I think one of the strongly appealing aspects of drones is the way they feed into our basic carnal instinct to be like gods, as Dr. Lanius so eloquently stated at the beginning of this course. Drones can evoke within us a sense of power and wonder, releasing us from constraints in new ways. And they can feed our narcissistic tendencies by making it easier to record more and more about ourselves. Now, perhaps surprisingly, most of drone technology isn't exactly new. The aircraft themselves are about the same as any manned aircraft. They follow the same laws of aerodynamics, structures, stability and control, propulsion, and vehicle performance. In fact, the US military has been experimenting with drones since almost at the dawn of aviation. In World War I, the US Navy started working on drones with Elmer Sperry, inventor of aircraft gyroscopes and father of Lawrence Sperry, who invented the artificial horizon. Sperry took Curtiss biplanes and installed his gyrostabilization systems to turn them into unmanned air torpedoes with a full load of TNT on board. These were designed to fly for a given distance and then dive towards a target and crash with great destructive power. Ultimately, these air torpedoes didn't operate reliably enough, and the conclusion of the war curtailed their development. Still, these ideas were the predecessor to the modern cruise missile. During World War II, a US company called Radioplane made drones that were used for target practice for anti-aircraft gunners. These radio-controlled aircraft could cruise at around 85 miles per hour for about an hour, making them the perfect expendable target for gunnery practice. And in an interesting twist of history, the future movie star Marilyn Monroe worked at the Radioplane factory and was spotted by an Army photographer doing a morale-boosting shoot on female factory workers. This chance encounter was the genesis of Monroe's modeling and acting career. In the midst of the Cold War, there was new impetus for developing drones following the downing of Francis Gary Powers' U-2 spy plane over the Soviet Union. That incident highlighted the need for an unmanned reconnaissance aircraft that would not make a captured pilot into a bargaining tool. This led to the development of the Ryan Firebee, which was used extensively in the Vietnam War to provide critical aerial imagery. As drones have become operational, the most critical technology is the radio link. It's the virtual tether that connects the vehicle to the ground, enabling the pilot to maintain positive control of the aircraft. If this link doesn't remain intact, the drone goes rogue and can behave in unpredictable ways. So the lost link situation is one of the most critical issues facing drone pilots. Modern drone aircraft rely on both direct line-of-sight radio communications for close-in operations of the drone, as well as satellite communications for long-range operations. The satellite communications links pose some interesting technical challenges. First is the inherent latency of the link. Even with the signal propagating at the speed of light, when it traverses the long distance up to space and back down to the drone, there can be a delay of about a second or so before the vehicle can respond. Another critical satellite challenge is increased risk for lost link. The antennas on board the drone need a clear view of the satellite in order to maintain the radio link. However, as the vehicle maneuvers, the directionality of the antennas will be out of alignment with the satellite, and the weak signal can be easily lost. Finally, a major technical challenge for any radio link is to maintain its security. If multiple drones are operating in the same vicinity, then there is increased risk of mutual radio interference unless some thoughtful strategies are employed to deconflict the signals. Also, the link can be susceptible to intentional interference or jamming. We can think of the radio link between the drone and pilot as the cockpit door of unmanned aviation. If any hostile actor tries to interfere with or even hijack the signal, then the drone can be drawn in under illicit control. Beyond the radio link, the other major technical challenge with drones is to maintain situational awareness for the pilot. Of course, it's easy to install cameras on board a drone, but even cameras provide only a limited view of the surroundings. I experienced these limitations firsthand as I did some drone testing at the Ohio State University Airport, collaborating with my colleague Dr. Matt McCrink. We were taxiing our unmanned Avanti jet around the airport while following instructions from the traffic control tower. In one instance, we were instructed to hold short of the runway threshold to wait for landing traffic. With Matt relying only upon the live video feed from our drone, it was extremely challenging to know how far our jet was from the runway, or to locate the landing aircraft until it was directly in front of us. Thankfully, we were operating from an observation deck that day, where we had a clear view of all runways and taxiways at the airport. But without that advantage, it would have been like viewing the world through a soda straw while attempting to avoid collisions. So this ability to detect other aircraft and obstacles in the vicinity of a drone is a critical technology challenge. This problem of collision avoidance is also referred to as detect and avoid, or sense and avoid. The main objective of detect and avoid is to successfully sense the presence of another aircraft, especially one that is on a collision course, and plan and execute an appropriate maneuver to avoid that aircraft. Since there is no pilot on board to ensure visual separation, the air traffic controllers and ground-based pilots must rely on technology to fulfill the detect and avoid requirement. So, what technologies and approaches are available for detect and avoid? Let's first consider the ADS-B transponder, which we discussed in the previous lecture. This can be a very effective solution, since all aircraft with ADS-B will have the situational awareness of other aircraft in the vicinity. However, there are some limitations, especially because the ADS-B mandate is not a universal requirement. For example, aircraft that fly away from larger airports and stay below 10,000 feet above sea level are not required to equip with ADS-B. So it is quite possible that a small drone could encounter a manned aircraft with no transponder on board. Also, the ADS-B system was never designed with drones in mind. The uncertainty of position reporting based on ADS-B requires fairly large separation bubbles between manned and unmanned aircraft. That would end up decreasing system performance, causing further delays to an already overstrained air transportation network. A different consideration is that if the system gets loaded with too many users on the same frequency band, then the system throughput diminishes and safety becomes compromised by less frequent position reports. So ADS-B is a very helpful technology for maintaining separation between aircraft, but it is not always available and may not be technically sufficient to handle all situations. Another solution is to install radar systems on board the aircraft to provide surveillance of the surrounding area. Radar systems are readily available on large-scale aircraft, which have the payload capacity to carry large radar equipment. In fact, all commercial airliners have a radar system on board to detect severe weather in the area. But small radar systems are also available, which employ a phased array radar, where the beam of microwave energy is electronically scanned in azimuth and elevation. These systems are small enough to be carried aboard even small drones, enabling even less expensive drones to detect and track other aircraft. Let's now pivot to small-scale drones, which first burst onto the scene in around 2013. The development of small-scale drones, such as quadcopters, has largely been enabled by the revolution of smartphone technology of the late 2000s. Three key technological developments for smartphones have been leveraged for drones. First, battery capacity saw rapid advancement in a short period of time. The energy density of storage devices, such as lithium-ion batteries, dramatically improved from around 100 watt-hours per kilogram in the mid-1990s to 200 watt-hours per kilogram in the mid-2000s. Meanwhile, the cost dropped dramatically, from almost $2 per watt-hour in the mid-90s down to less than 50 cents per watt-hour in the mid-2000s. Second, the cost and performance of inertial measurement units, or IMUs, have dramatically improved over the same time period. These IMUs are the same devices used in the glass panel avionics for manned aircraft. However, the smartphone revolution pushed the development of miniaturized electromechanical technology, driving down the cost of IMU technology. So, for just a few dollars, IMU sensor suites with 3-axis accelerometers, 3-axis gyroscopes, 3-axis magnetometers, and pressure transducers are available. These sensor suites allow the unmanned aircraft to maintain stable flight with precise determination of vehicle attitude. Third, the continual evolution of global navigation satellite systems, such as the American GPS network, or the Russian GLONASS system, has allowed high-precision positioning. While GPS has been around for a while, low-cost chipsets with low power consumption are now commonplace due to the smartphone revolution. So, the development of this seemingly unrelated technology of smartphones has propelled technological innovation that has enabled small-scale drones. Now, there are some really interesting aspects of scaling that come into play when we look at small-scale aircraft. First, small-scale drones are much more maneuverable than large manned aircraft. The reasons are that they are much lighter and have much lower moment of inertia. Now, whenever mass is concentrated closer to the axis of rotation, the moment of inertia about that axis decreases. And bodies with a lower moment of inertia can rotate much more rapidly. This makes for some really exciting, fast-paced action as tiny, highly maneuverable drones race each other. Drone racing leagues form a venue for this sport, where pilots maneuver their highly agile small drones through a twisting and turning course with the help of a first-person video. The vertigo-inducing images that they see are surreal, like the pilot has a disembodied view of the world. But this higher maneuverability comes at a cost. Small drones are much more susceptible to wind gusts. As we discussed in our lecture on structures, when the wing loading of a vehicle goes down, the amount of load factor induced by a given gust goes way up, and the lift produced by the rotors is related to the wake development underneath each rotor. If a strong wind gust disrupts the configuration of the wake, the bottom can drop out on the vehicle. The impact of wind gusts is one of the key challenges to operating small drones in an urban environment. When multiple tall buildings are present, an urban canyon effect can be present, where wind flowing over and around the buildings results in strongly gusting conditions within the canyon corridor between them. This can lead to unsteady downdraft gusts that have a speed several times that of the average wind speed. So a drone operator flying along that doesn't anticipate these gusts could be in serious trouble. The aerodynamics of small-scale flyers is also much more challenging. With the characteristic length scale of the drone, say its rotor diameter, is small, then the viscous effects of air become much more significant. The viscous effects alter the location of separation on the blade, which drives up the power requirements for the drone to hover. Now, many of the smallest drones, called micro-air vehicles, actually exploit the unsteady viscous effects of air, just like birds and insects do. Flapping wings actually allow the dynamic separation event to occur. The separated flow rolls up into a tornado-like vortex over the wing, which induces locally high-speed flow, and with it, low pressure acting on the wing. Flapping wing flight can actually be a more efficient approach for these small-scale flyers. One of these is even made to look like a hummingbird for use in close-in reconnaissance. With small-scale drones capable of flying well beyond an operator's line of sight, there are key technologies that enable them to fly safely. Here, the requirements for safety are accurate navigation and collision avoidance. Let's take a look at each of these in a little detail. For navigation, many people assume that GPS is a final solution to allow safe flight of aircraft. What else could we ask for? GPS gives a vehicle's position and speed. That's really all we need to know, right? Well, there are certain situations where GPS is not reliable enough. For example, following the same idea for an urban canyon with wind gusts, there is an urban canyon effect for GPS. This happens when the signals from satellites are reflected off of adjacent buildings and the receiver picks up multipath signals, in addition to the direct line of sight signal from the satellite. Since GPS depends on the time of flight of that signal, multipath reflections result in errors in the computed position. Also, since GPS relies upon weak signals, it's not difficult at all to jam a GPS signal by transmitting an interfering signal. This is actually a problem that commercial aviation also faces. There have been numerous reports of aircraft losing their GPS lock while on short final approach at Newark International Airport. It turns out that the cause of that GPS dropout was truckers driving by on the adjacent highway who were carrying GPS jammers, designed to jam their own GPS signal so that their corporate operators wouldn't know how fast they were going. And finally, if we ever want to operate a drone indoors, we have to rely on some other positioning scheme since GPS signals won't penetrate the walls and ceilings of most buildings. So what can be done in an environment where GPS is degraded or denied? Well, drones have built-in inertial measurement units that allow them to determine their instantaneous orientation. These inertial measurement units, which are also in every smartphone, are a tiny suite of sensors that include a magnetometer, gyroscopes, and accelerometers. These sensors provide information about the magnetic field, angular rates, and accelerations experienced by the drone along all three axes. The three-axis magnetic field data is useful since it provides insight into the orientation of the vehicle within the Earth's inertial frame, basically indicating direction, just like a compass points to the North Pole. The rate gyros are tiny versions of the mechanical gyros that drive traditional aircraft instruments like the artificial horizon. These provide instantaneous rotation rates about all three axes. And the accelerometers give the vehicle's linear acceleration along all three axes simultaneously. These three datasets can be fused together, and using the basic principles of Newtonian mechanics, the vehicle's acceleration and angular rate can be integrated over time to find where and how the vehicle has moved from its starting point. This is the same idea for navigation that satellites and submarines use, since they also operate in environments where GPS is denied. The challenge, though, is that errors crop in that lead to divergence of the computed position as time goes along. These errors depend primarily on the sensor noise, but there are aspects of the numerical integration that also drive the divergence. The other strategy for inferring a drone's location without using GPS is to rely upon vision systems. There are techniques to recognize features in a scene that has already been mapped. And there are optical flow techniques, which allow the motion of the scene perceived by the sensor to be used for extracting vehicle motion. Some of these ideas actually spawn out of the biological realm, as researchers have studied insect flight, which is based on low power and sparse sensors. They have gleaned ideas for implementing optical navigation schemes within the small-scale, lightweight, and low-power packages demanded for small-scale drone operation. Now, throughout the course to this point, we've been talking mostly about how fixed-wing aircraft fly. But with vertical lift quadcopter drones being very popular, we need to know something about how helicopters generate sufficient lift. In our next lecture, we'll focus on all things related to vertical flight.